My name is ID Sufyan. So I explain about what is the transfer function. The transfer function H omega is defined as the frequency dependent ratio of the phasor output to the phasor input. H omega equal Y omega divide S omega. Y omega is phasor output, voltage current, and S omega phasor input, voltage or current source. Omega is angular frequency where omega equal 2 pi f. H omega is a complex quantity that describes how a circuit responds to sinusoidal signal at different frequency. It provides information about both the magnitude and phase of the output signal relative to the input signal. Key properties of H omega. The transfer function H omega is a complex frequency dependent quantity that fully characterizes how a circuit responds to a sinusoidal input. It can be expressed in a polar form as H omega equal H omega less theta omega, where the magnitude and the phase is carry distinct physical meaning. First, frequency dependent response varies with omega. Second, complex quantity H omega equal H omega less theta omega. Third, magnitude H omega gain of attenuation. And last, phase theta omega shift between input and output. Common application H omega. Transfer function appear in many forms depending on what quantity are measured at the input and output of the circuit. Each application below represent a specific ratio of phasor quantity, enabling frequency domain analysis of different circuit behavior. First, voltage gain H omega equal V out omega uh, divide V in omega. Second, current gain H omega equal I out omega divide I in omega. Next, independence Z omega equal V omega divide I omega. And last, admittance Y omega equal I omega divide V omega.
So, moving on to the core analytics method, how exactly do we study a circuit's transfer function in practice? We primarily rely on three fundamental tools to evaluate frequency response and system behavior. First, spot plot. These are highly intuitive graphs that display the magnitude in decibel and the phase angle in degree against a logarithm frequency scale. This allows us to observe a system behavior across a massive frequency range at a glance. Second, plot zero plots. These plots map out the complex S-plane, showing exactly where our system poles and zeros lies. This is critical for characterizing system stability and resonance. Third, Nyquist plot. By tracing the complex locus of H omega, as omega vary from 0 to infinity, Nyquist plot provide a rigorous checks for both open loops and closed loop control system stability. We are given the transfer function H omega plus equals to 50 j omega over terms j omega plus 4 and j omega plus 10 square. So now, to analyze this using Bode rules, our first goal is to convert every linear factor into standard form, which is looks like bracket 1 plus j omega over omega c, where is omega c is our corner frequency. For the first term in the denominator, the j omega 4, we factor the 4. This gives us the 4 in bracket 1 j plus j omega over 4. For the second term, which is the double pole, the j omega plus 10 square, we must factor out the 10 or 100s. This leaves us with 100s, 101 plus j omega over 10 plus square. By substitute this back into our transfer function, the denominator constant multiplier becomes 4 times 100s. This must simplify our overall system gain coefficient to fraction to 50 over 400s, which reduce cleanly to a system gain of 1 over 8. Now, once we have our fully simplified standard form equation, which is uh, omega, h omega, and 20 log power of 10 and 1 over 8 equals to negative 18 decibel. Now we can extract the vital parameters needed to construct our hand-drawn plot plots. First, the system gain. Our gain constant is 1 over 8. To find its baseline contribution on the decibel plot, we calculate the 20 logarithm 10 by 1 over 8, which gives us approximately by negative decibel. This shifts our entire magnitude baseline downward. Zeros. We have simple zeros at the origin due to the omega j omega in terms in the numerator. This introduces a steady initial outward slope of positive 20 decibel per decades, starting from the very low frequency along with a constant initial phase lead of positive 19 degrees. Poles. In the denominator, we identify two distinct corner frequencies. A simple pole at omega for RADs, which will introduce a downward slope change of negative 20 decibel per decade. A double pole at omega 10 rads per second, because it is square, it is exact twice the influence, pulling the magnitude plot down by an additional negative 40 decibel per decade and introducing a significant phase lag. With this component clearly defined, we can confidently move on to plotting our exact magnitude and phase response.
Okay, my name is Afkar Nakidin Azman. My matrix number is B1125107121. Okay, now moving on to our magnitude response of the system, which you can see the outline step by step in this slide. To construct and verify our magnitude plot, we follow a structured 5-step process. Step 1 is identifying our core component. We have our gain factor K, a 0 at the origin J omega, first pole, P1 at 4 radian per second, and a second pole P2 at 10 radian per second. In step 2, we look at the low frequency behavior below 4 radian per second. In this region, only the 0 and the gain dominate. The 0 gives us an upward slope of plus 20 dB per decade, while the gain contribute a flat 0 dB per decade, resulting in a combined initial slope of plus 20 dB per decade. Moving to step 3, between 4 and 10 radian per second, our first pole at 4 radian per second activates, because a simple pole introduces a negative 20 dB per decade slope. It perfectly cancel out our initial plus 20 dB per decade slope from the 0, flattening our net slope out to exactly 0 dB per decade. In step 4, at higher frequencies where omega bigger than 10 radian per second, our double pole behavior dominates. The addition of the second pole drags the slope down by an additional negative 40 dB per decade. bringing our final line down sharply at negative 40 dB per decade. Finally, step 5 is all about verification. We cross-check our manual plot against specific mathematical verification points, such as at omega equal to 1, 4, and 100, and found that our graphical representation exactly matched our calculated values, proving our plot accuracy. Okay, now let's transition to our bode plot analysis, bode phase plot analysis. Let's look at now at how the phase angle of our system responds across different frequency regions as shown here in the slide. We can break down this phase plot into our 4 distinct frequency zones. First, at very low frequency, specifically where omega is less than 0.5 radian per second, our total phase stays flat and starts at a solid plus 19 degree. This initial shift is driven by the zero in our system. Next, we hit phase region 2, which covers at first drop between 0.4 and 1 radian per second. Here the slope begins to decline at a rate of negative 45 degree per decade. Then come region 3, the steep drop between 1 and 40 radian per second. The downward slope accelerates significantly to negative 135 degree per decade as the system pulse really start to kick in. Finally, in region 4, at high frequency where omega is greater than or equal to 100 radian per second, the system stabilizes. The total phase levels out and settle completely at negative 118 degrees. This completes analysis for the magnitude and phase characteristics of our system. I will pass it over to the next presenter.
Thank you, Amirul Hakim. In this slide, I will explain the analysis of the bode plot for transfer function and how the system transfer function can be determined from its magnitude response. First, let us observe the low frequency region where W is less than 1 radian per second. The plot starts with a slope of negative 40 decibel per decade. In bode plot analysis, a slope of minus 40 dB per decade indicates the presence of two poles and the origin, which is known as a double pole. Therefore, we can identify the term in the denominator of the transfer function. Next, we move to the first corner frequency at W equals 1 radian per second. At this point, the slope changes from minus 40 dB per decade to minus 20 dB per decade. This represents a net increase of plus 20 dB per decade. Such a positive slope change indicates the existence of a single zero. Therefore, a zero is located at W equals 1 radian per second, represented by the factor in the numerator. Then, at the second corner frequency, W equals 10 radian per second, the slope decreases again from minus 20 dB per decade to minus 40 dB per decade. This is a net change of minus 20 dB per decade, which corresponds to a single pole. Hence, we identify a pole at W equals 10 radian per second, represented by the factor in the denominator. To determine the system gain, K, we use the magnitude information from the low frequency region. From the graph, the magnitude is approximately 20 dB at W equals 0.1 radian per second. Substituting this value into the magnitude equals giving a gain of K equals 0.1. Combining all identified components, namely the double pole at the origin, the zero at W equals 1, the pole at W equals 10, and the gain K equals 0.1, we obtain the transfer function. In conclusion, the transfer function is successfully derived by analyzing the slope change and corner frequency of the bode plot. This demonstrates how bode plot analysis can be used to identify system pole, zero, and gain directly from the frequency response. This assignment highlights how effectively transfer function and bode plot describe a circuit frequency response. We verify that poles reduce gain and introduce phase lag while zero provide phase lead. Mastering these analytical tools is incredibly vital for anyone looking to design filter, audio equipment, or complex electronic systems. That's conclude our presentation. Thank you very much.